talk about an AI that does lean and proves theorems. Yeah, Alex, you can unmute yourself. Yeah, let's go.
Great. Yeah. Thank you very much, Remy. And thank you to the organizers for putting together such a great conference as always. So yeah, I'm going to talk about a sort of an AI theorem prover that the team at Harmonic have been developing for the past, well, I guess almost 2 years now. And yeah, this is really a system aimed to automate the process of, well, first of all, proving things in lean, but more generally, uh, proving things, right? So finding new proofs, automating the process of mathematical discovery, accelerating mathematical research, and applications to similar domains. So things like verified software. So I think we're have big goals, and we're excited that we now have a system that the people in the lean community can now use, and that's what I'm going to kind of talk about today. So I want to kind of start at the kind of well, I'll start with the outline, which is that computers can prove non-trivial theorems in systems like lean. So I'm going to start with some sort of examples of basic theorems that computers can prove that you might consider AI, you might not, and I'm going to kind of work up to the things that Aristotle can prove, just to kind of understand the difference between the sort of level of autonomy that these systems have. And so recent systems like Aristotle can produce sort of multi-thousand line formal proofs on their own, and that is, I think, going to change the way that we do formalization, and we should think hard about that. So I'd spend maybe a slide or two at the end kind of discussing a little bit the way that the contributions to libraries or projects might change with the advent of these technologies, and sort of what adjustments we might need. So yeah, let's start at the beginning. So there has been sort of bespoke automation in lean and in other proof of systems, of course, for many years. And so these are things that essentially implement a pretty well-described algorithm that apply to sort of a narrow class of problems. So a great example of this would be linearith or n-linearith. They're highly reliable when they apply, but they're in some sense extremely specialized. They work on a fixed class of problems. So for example, if you take the ring tactic, that will work in commutative rings, and it will prove equalities that are true in arbitrary commutative rings, but only those. It will never be able to do sort of anything more than that, because it's essentially just executing human written algorithm. Nevertheless, they're extremely useful, right? So this is a quite a complicated example of actually a misformalized statement, where we can see that sort of by applying n-linearith, the version that also handles the fact that squares are always positive and kind of improves upon linearith by using that, when supplied with a large set of arguments, can essentially prove extremely non-trivial statements by kind of expressing things as sums of squares, right? This is kind of a classic technique for proving something is positive, is express it as a sum of squares. So even though that they're kind of bespoke, they can be really powerful, especially when sort of fed the right arguments. It's just maybe sometimes tricky to work out what the right arguments should be to really unlock the power. So here are some examples I found of really complicated calls to n-linearith that take sort of several lines, and you maybe wouldn't think of when immediately looking at this problem. So that was kind of the first level. I think the scheduling has been extremely good, because we just heard Kim talk about grind for half an hour. So, well, I'm a little bit behind on the curve because I'm not using grind's interactive mode. I'm just using the non-interactive version. But this is sort of one level above, you can think of. It's more extensible because it's, as was mentioned, extended by sort of tagging, definitions, and library lemmas. And in that sense, it's maybe not a set in stone exactly what the specification of this algorithm is. And because it uses a variety of other procedures as sort of internals, you could consider it as a sort of a higher level building block, right? So this grind tactic in theory should handle anything that linearity could have, right? So the main issue, I think, with grind, for example, and things that are at this level is they're still a little bit opaque, right? It's very hard to know ahead of time if a given call will succeed. Of course, there'll be some simple situations where you know they will succeed, but in many situations you'll just kind of try it out and have a go, and maybe there's some annotations missing, and because of that, grind will not succeed in a situation where it ostensibly should have, right? So this is a really nice example. There is a very funny blog post that I've linked to at the bottom here, basically proving versions of this statement that insertion sort is correct in about 500 different ways. And this is meant to be, I think, one of the cleanest and most enlightened versions, which is to tag your definitions with grind, do induction and prove the cases with grind, and that sort of proves a relatively non-trivial statement, which is very cool. So that is kind of I guess you would say, the state of the art of kind of deterministic automation for lean. So the next level up, I would place these AI systems. So these are systems that instead of applying sort of maybe extensible but still kind of hard-coded set of rules, suggest steps by sampling from neural networks, right? So they are sort of probabilistic systems that in principle are capable of producing sort of arbitrary proofs, because there will be some probability that they'll produce arbitrary proofs. Of course, it may not be high, but in that sense, they are completely general, if sufficiently powerful, right? So these are developed not by hard coding them, but they're developed by sort of learning either from sort of freeform data or better yet, from experience. And in that sense, they kind of aren't designed, they're more sort of grown, right? So with these systems, you don't sit down and kind of describe what sort of problems it will solve and how exactly it will function. You simply provide lots of examples during its training to kind of hopefully have it learn when to do certain things, and essentially learn internally which algorithms should be applied. So because of this sort of generality and not needing humans to kind of write the code, they're able to solve extremely challenging problems, and they're way more general, and can operate productively, autonomously for far longer periods of time. So yeah, they're often more flexible than kind of bespoke automation or handwritten procedures. And because they are, at least in the case of harmonic based on language models, they make interacting with a formal system like Lean much closer to interacting with a human, right? Because they understand natural language as well as Lean and kind of interpolate between the two. So one thing I'd like to highlight here is that they may use things like grind and linearity as building blocks, but they build kind of higher level abstractions and structure on top of them. So maybe it won't surprise too many people to realize that the example from the first slide was, of course, written by Aristotle. No human writes n-larith calls like this. Maybe they prefer to write a sequence of have statements instead. But this is kind of the I don't know, Matryoshka kind of this principle where it's not that we're replacing bespoke automation. We're building sort of a higher level interface on top of these things. So yeah, we kind of need this kind of stack of kind of highly specialized automation, more general automation, and kind of AI on top to kind of get the best results. So they shouldn't be seen as kind of like strict domination of each other, but really like a kind of a stack where each step works at a high level. So what is Aristotle? Aristotle is a AI system of the sort I just described. It's a large language model based system for theorem proving in Lean. So it's trained by reinforcement learning on Lean feedback, and it's capable at this point of kind of developing basically entire projects autonomously. It can produce many thousand line files. It can add new definitions and structures, and add API lemmas. And so, yeah, when prompted, it's more similar to kind of working with a coworker than calling a tactic. It can work for sort of many hours. I'm happy to say that it's like now available to everyone via aristotle.harmonic.fun. There is no longer a wait list. Anyone can go to that website and sign up and get an API key. And then they can be presented with a nice terminal interface like this, where you have several options. For example, filling in the sorries in your lean file, which is, of course, something we all enjoy doing. Another one is to kind of feed it a text file or a markdown file or a text file or just something with some kind of informal content and ask it to auto-formalize it. So this could be as simple as a, TXT file with a few sentences in describing your new idea, or it could be your latest paper that you just uploaded to archive and you want to check. And the final version is sort of more freeform. It's just to kind of direct it with some prompt like, develop the theory of quasi-Fubon modules or something, and just to kind of provide minimal direction, but still hopefully produce a lean file that contains something interesting. So I won't give a demo live because this talk is a bit too short, but I really encourage everyone to go and try it out. And I'll now describe some sort of like user experience reports. So some things that people have done with Aristotle that I think are really cool and compelling, and I hope really kind of inspiration. So by now, many people may have heard, but the sort of Erdos problems have generated a lot of excitement amongst not just mathematicians, but actually a sort of a wider audience. So Erdos, of course, was a prolific mathematician who produced many hundreds or thousands even of papers, many of which contain question marks. And Thomas Bloom has taken it upon himself to convert all of these kind of suggestions into well-specified problems that the community can kind of work on collaboratively. So this is a website called Erdos Problems, which is kind of a highly collaborative, really exciting kind of venue where people kind of suggest ideas, people are applying AI tools, and kind of as a collective, people are kind of trying to dispatch as many of these problems as possible. So people using Aristotle are also extremely prolific on this website, and they're using Aristotle to find both novel proofs, to auto-formalize kind of informal sketches, and if there are kind of oversights in informal sketches, to kind of correct them. Maybe they'll kind of formalize a special case, and from that proof, they'll derive some new insight that kind of leads to a general case. So this is really a kind of a collaboration happening here between humans and AI, which is very exciting. So I put a couple of links there at the bottom, which describe a couple of kind of interesting storylines that have played out on this site. And I think by now there's actually kind of too many for me to even remember and name. But people like Boris Alexeyev have really been using Aristotle to great effect to kind of solve some of these problems or to check solutions. And they are making great progress. So Boris, for example, has kind of basically written a script that uses Aristotle, and he's now written in collaboration with Aristotle over 90,000 lines of lean code with solution to kind of Erdos problems and various other kind of problems. And these are really a mix of kind of auto-formalizations of old proofs, maybe new proofs of old problems, new proofs of new problems, really kind of every part of that Venn diagram at this point, I think is filled. And I would say that it is basically impossible for one person to have produced this project on the same time scale with sort of 90,000 lines of basically research level mathematics, fully formalized in lean of non-trivial problems over the past couple of months. And I'm sure Boris has a sort of a day job as well. So this is extremely impressive. So many other people have been, auto-formalizing their papers in real time. So here's one example of Bartosz Nastrecki, who, I think he was inspired in this case by some game he was playing to create the following kind of group theory problem that maybe expressed a general solution to a game. And, he basically at the same time as writing his paper was able to auto-formalize it. So this is the sort of thing that I think we've all dreamed of for some time, but it is now really possible that you can kind of write your tech and you can have a machine working in the background, converting it into a formal proof, and telling you which parts are correct and which parts need some revision. So just as an example, I mean, this is the final statement from his tweet, and this is line, I think, 2,600 of the file. So, his paper, I'm not quite sure how long it was, but it turned into a, almost 3,000 line lean file, and, he didn't have to write any of it, which is quite cool. So Tao has, recently been trying to sort of make explicit a lot of the estimates that appear in analytic number theory papers. And Pietro Montecone has been using Aristotle to accelerate this project in several ways. So what I'd like to highlight here is that, it's not just proving things, right? Aristotle has been finding counterexamples for misformalized statements, counterexamples which you probably wouldn't, in this case, the counterexample was not the classic, x equals 0 or -1 or something like that, but a kind of a non-trivial edge case in one of these statements. It's been used to kind of vet definitions. When Aristotle returns, and it returns a proof which seems too trivial, right? In this case, there was a proof of a non-trivial statement that Aristotle proved via Bertrand's postulate. And for people who kind of know number theory, Bertrand's postulate is one of the kind of the first ever estimates you really can make about the density of primes. And so to prove something non-trivial using it, you kind of know that something has gone wrong. So in this case, it was found that a definition was made too weak. And a human was able to realize that by virtue of seeing a too simple proof come out of Aristotle. It's, as always, finished off sort of entire sub-projects of this project on its own. And it's been used to kind of fill in some of the results that probably humans are interested in, but maybe would not have actually bothered to take the time of themselves. So it's sort of driving older bounds, which are weaker as consequences of newer, stronger ones, kind of validating that the statements are correct. And humans probably wouldn't have bothered to do this themselves, but it's kind of a nice stamp of quality that we're not accidentally kind of introducing false stories into the project. So that was a bit of a kind of grab bag of examples. There are many other kind of applications that I don't really have time to mention, but I would also highlight that system is also very capable in software verification tasks. So given goals that sort of prove things about programs written in Lean, and that's sort of that nature, the various different ways of kind of doing that, we also find it to be quite effective. So I would encourage anyone who's interested in software verification not to be dismayed that all of my examples were in mathematics. That's just a fact of not quite having enough time to cover everything. So how does this work? What has been the transition from kind of maybe a couple of years ago when people were kind of talking about AI kind of tools for lean proofs, but they weren't yet at the scale where they could really be of assistance to humans in the majority of situations. I think the main driver of recent progress has been reinforcement learning. So of course, I don't have time to really go into the details of this, but the idea is that instead of training on sort of human examples, you primarily train a model sort of by experience. So you give the model, this is a large language model, some sort of reward for doing the correct thing, and then you ask it to go away and try things out, and you kind of sort of upweight all the things that it did that led to a positive reward. And so what this means is that you no longer need human examples of how to do all the different proof styles. All you need is a collection of problems for the agent to try out. So this means that you can kind of basically be completely hands-off after a certain point and kind of let the model continue to teach itself, which is an incredibly sort of powerful paradigm to be in, right? Once a system is written, there is less human intervention needed to kind of increase the capabilities, kind of basically autonomously keep increasing in capability, which is certainly what we're seeing and what we expect to continue to happen. So in mathematics, you could do many different types of rewards. Reaching a correct numerical answer could be rewarding. Writing code that compiles and produces the right answer could be rewarding. Producing a proof that convinces another model or passes some sort of rubric, could be a good thing. And finally, producing a lean proof that solves the goal could be a good thing. And harmonic, we're really focused on the last one here. I think we believe that, lean is as a kind of perfect verifier for reasoning is the ideal way to teach these models how to do mathematics. And so, although I think the others have a lot of value, we're really kind of deeply embedding our training into lean itself. So this kind of turns the problem of proving theorems into a game that the models learn to play better and better. So we have an archive paper which came out, I guess, a few months ago now, describing the system that we deployed at this year's Math Olympiad, which kind of got 5 out of 6, which is a sort of a gold medal performance, more or less, in the competition. So I'm going to describe a little bit how that system worked. The system that we deploy today is, of course, new and improved. Beyond this, we're improving it all the time, but this should give some flavor of how things work. So in this system, there were kind of 2 main subsystems. There was a proof search system, which searched for kind of filling in sorries via what's called Monte Carlo graph search. And the system suggests new lemmas and kind of do high-level planning and kind of reject lemmas and formulate proof strategies based on which lemmas turned out to be true. So you can imagine a lean proof whenever you put a sorry being kind of a new node in a graph. And so suggesting tactics which contain sorries, you can think of as kind of walking a big kind of graph of potential lean states. And that's exactly how the kind of proof, the sorry closer works. The model suggests tactics and it explores a graph essentially. And when you get to a point where there are no sorries remaining, you found a proof. So there's a language model which is suggesting tactics, and other parts of the system kind of prioritizing different parts of the graph. As I mentioned, there's kind of a separate system that kind of sits around the proof search, which formalizes lemmas and kind of revises them and kind of does that in a loop and kind of lets us kind of take this kind of graph search procedure, which is quite powerful, and kind of lever it a lot into something which is producing entire files or entire theories. So I won't go too much into detail because I'm low on time here. I know we started a couple of minutes late, but I really don't want to go over. So I would like to very quickly encourage people to think of these systems more as sort of AI co-workers or junior collaborators. Instead of kind of starting, proving your theorems kind of lemma by lemma or working backwards, think about what's the minimal amount of description you need to give to your new coworker to successfully formalize the problem, and take on more projects, do them all in parallel, and manage your team of coworkers effectively, and kind of accelerate this development of kind of formal mathematics to the point where it can be sort of genuinely useful for research mathematics. I think that's been my dream personally for many years, and I think this is really the only way we're going to get there in a reasonable timescale is by kind of embracing these new tools. So that's my kind of exhortation to you, and I want to see this MATLAB kind of growth graph go like this. That would be my dream. And in order to do that, I think we're going to have to consider how we integrate these new proofs, right? We have kind of a big fountain now that's producing many lean proofs that we need to integrate. I think we need more automation inside of the libraries to kind of ensure that the proofs are high quality and ensure that they're integrated in a timely manner. And so I would encourage people to think about that a bit more, and to use these tools. So thank you very much for your attention. I'm going to stop there just to leave some time for questions.